one of the things that we'll want to talk about in many situations, many real-world approximations, is what the electric field is from a very, very large plane, or an infinite plane. Plane meaning flat surface. Now, to get here is a little bit tricky. You could just try to break it up into point charges and do some integration, but the approach we're going to take is looking at the disk, which was in the last video, and simply say that we're going to take the radius to infinity. Now, something that some students get a little bit stuck on is that frequently our infinite planes, you might want to think about them as square planes. But here we're taking a disk, which was circular, and say its radius goes to infinity. Fundamentally, if it's an infinite plane, you can't see the edges. So if you can't actually see the edges, can you tell if it's circular or square? No, you don't see the edges. So that's why it's okay that we're going to actually derive this from the circular case and then generalize it to any situation where we aren't worried about the edges. So this was the exact form of the electric field from a disk of uniform charge when we are on the axis of the disk. So we want to take the radius to infinity. And all we have to do is say in this case, well, that goes to infinity. So this is effectively gone. Z divided by infinity for Z is any value over that is not infinite. This whole term goes to 0. We have then 1 minus 0, which is 1, so we're left with eta, which was our surface charge density, divided by 2 epsilon naught, where epsilon naught is our constant. Note what's happened. This is now independent of position. Z is completely gone. And this is actually quite striking and requires a little bit of interpretation. This mathematical result tells you that the electric field from an infinite disk, a plane, is independent of how far you are from the surface. And this is something that initially should be counterintuitive. It should not make sense. But ideally, you should be able to think through it and, one, believe in the math, and two, try to understand what this is telling you. This is a case where the math can lead your intuition if your intuition is wrong. So the reason that this is working is that, again, it's an infinite plane. We can't see the edges. There is no length scale whatsoever. So, for instance, if I put an ant on a balloon, to the ant, the balloon is very large. But to me, the balloon is very small. Why? Because I am serving as the length scale myself, right? The balloon is smaller than me. The balloon is bigger than the ant. Well, an infinite plane has no length scale. It has no thickness, and because we're assuming that it's infinitely thin, and there's no real length to talk about. So if you woke up on a spaceship and you seem to be on the ocean and you started taking off away from the ocean, I guess it was a floating spaceship. As you got farther and farther away from the ocean, the only way you could tell that you really were getting farther away is either that you could start seeing new things on the horizon, or that you can see waves on the surface of the ocean getting smaller. Well, what if there was nothing new on the horizon? And what if there were no waves? Once you were off the surface, you really wouldn't be able to see that you were getting farther from the surface. Now, this is something hard to wrap your mind around because we've never had this experience, that in the world around us, there are always features that really determine a length scale. But a pure ideal infinite plane, that's not the case. So because there's no length scale, this also means that this is going to be true for all locations. Here, for the disk, we had to be on axis. We had to be in the center. Well, there's no axis of an infinite plane because there is no center, right? If it's infinitely wide, and I say, well, I'm in the center right now, there's an infinite length to the left of me and an infinite length to the right of me. I now walk 10 feet to the left. Well, there's still an infinite amount to the left of me and an infinite amount to the right of me. So there's no axis. This is true for all locations. So what does this actually look like? So what we would say is that the magnitude of the field, the strength of the field, is eta, that surface charge density, divided by 2 epsilon naught. And again, you have the same strength no matter how far you are. So if we think about this edge on, remember this is not a wire, this is not a line of charge, this is an edge view. That's important. That every vector, and it could keep going out and out and out, it just ends at this point, but every vector is the exact same size, both to the left, to the right, and up and down, because this does not depend on position, and it's true for every position. If we actually tilt it on its side, you can think of these as field lines or field vectors, but it's a little harder to see what's going on in that case. So this edge view is a little more helpful. Now, the direction is perfectly away for positive charges, as both of these show, but if it's a negative charge, you want to make it towards. So all of these would simply flip around. So to speak a little more about the representations, again, this is an inherent three-dimensional view, and this is our edge view. In both of these cases, we've had to truncate it because the page itself ends, right? Like, I can't actually draw an infinite figure. So be careful that you don't interpret this as a literal edge of our infinite plane. Once we say it's an infinite plane, well, this edge isn't true then. We just have to show it in some way. So I encourage you to use an edge view, but make sure that you're clearly labeling things. The other reason to do that is, again, we know that if this was a wire, the electric field would actually be decreasing as we got farther away. So please make sure that it's clearly labeled, it's clear to you, and keep in mind that frequently both pictures I'm going to draw and then pictures you're going to draw, even if it should extend to infinity, we can't really draw it that way.